talk about resilient drone autonomy in a challenging urban environment, I present to you Dr. Abdul Ghani Mohammed.
Thank you very much, El, for the introduction. I'll just share my screen. As introduced, my name is Abdul Ghani, and I'll talk to you today about, the enabling the resilience or increasing the resilience of drones in our urban environments. And that is one of the challenges of having sort of, a fleet of drones operating routinely in our urban environments. So before we jump into that, I'll just quickly give you an overview of who I am and who I represent. So I'm part of a research team at RMIT University, and we are dedicated to trying to identify technologies and undertake research that enables safe and routine operation of drones or unmanned aircraft systems for a number of applications. So we are, about 4 academics, 12 PhD students, 2 masters, and an increasing number of undergraduate students working in this area. And we have worked across with various industry partners and trying to enable this technology. So starting off basically with, our growing cities. They are growing, not horizontally, vertically. And that produces or presents an opportunity in terms of savings in both time and money. So thinking about, for example, the person living at the penthouse at the top there, there is an opportunity to potentially grab an air taxi, which is a concept that's being pushed at the moment and is of very high interest to a number of, companies. And there is a potential to grab an air taxi to go, for example, to the airport. And instead of going through normal streets, which would take time and through congestion of traffic. There is also the opportunity of getting your food delivered to your penthouse at the top of that building instead of taking the elevator, which takes a few minutes and so forth. So there is that sort of growing market as part of something called urban air mobility. Now, this presents opportunities and also presents challenges. One of it being that the neighbor next door in that penthouse or the level beneath you is probably not going to enjoy the noise of a drone or an air taxi operating, and that noise is quite a big issue for that technology and adopting that. So it has been a problem for even standard aircraft or residential houses around airports. So it is now that drones are sort of routinely operating in urban environments. And for example, here in Australia, we've got Canberra as one of the leading cities that has drone delivery service operational. One of the first things is that there is a very increasing and large number of complaints from residents for noise. So the challenges, that are associated, some of the major challenges include turbulence. So you've got this structure that's basically obstructing the flow. And that does what that induces into the flow field is mechanical mixing. And that can be quite challenging and has led to accidents before. So there is that component. There's also the problem of energy density. So our batteries aren't still at the stage of, for example, animal fat in terms of the energy that it can store, which means that these aircraft, they have a relatively shorter range than we would like. So we have that being a problem, meaning that your network or your operational fleet cannot go very far, depending on the configuration and so forth. And lastly, the noise problem that we talked about. So we actually work across those 3 areas, in addition to other areas as well. So starting off with the turbulence aspect of things, I've got a chart here, which I'll go through slowly explaining. Any control system has what's called a sense, plan, and act cycle. So a control system responds by sensing, for example, a disturbance, in our case, a drone sensing a disturbance of turbulence or the flow field, and then it computes or processes what that signal means and how it's going to use it. And then you've got, the act aspect of that cycle, so the actuation. So how it uses, the sensed and the processed sensor output to produce a counteracting effect. So in addition to that, you've also got the block here at the start, which is the, let's see if I can use my little laser pointer there. So you've also got the turbulence as a block. So understanding what that disturbance means. So we've worked across all those sort of 4 blocks, and you can see that, you know, on this image here in this little video, you can see that we've explored some pressure-based sensing instrumentation that we can utilize on aircraft to try and basically predict before it causes an inertial response to the aircraft, predict what the disturbance is going to be. So we've looked at that. We've also done some research with respect to different control architectures. We've also found that the biggest problem with such control systems or autopilots for drones flying in highly turbulent environments is that the actuation has the biggest time lag. So from the time you sense a disturbance to the time you compute it, there's not much time lag, but the most of the time lag is sending that command to actuate and correct for maneuvers by the drone. And we have looked at that aspect, and I'll talk through that in shortly. So we have looked through that aspect and look at novel configurations that can help reduce that. Here you can see a drone in a wind tunnel facility looking behind it, and it's doing basically control loops in there. But one of the things I'll lead to as well is trying to learn from nature how they and how birds were able to mitigate turbulence. And we'll talk in detail, but some species of birds are basically very well adept to mitigating turbulence and very high levels of turbulence. So looking at doing some learning from nature. So starting off with the first block, which is the turbulence block there. Some of the work that we've done was to basically understand the flow field around an urban environment. And one of the things that we have at RMIT University is this unique building in one of our campuses, which, as you can see here in the image on the bottom right corner, it's quite a cuboid building, and it's the only building that's sort of sticking out in that sort of suburban environment. And that gives a unique opportunity to undertake significant flow experiments to try and understand the flow field in there and undertake full-scale experiments. So what we've done was we've used something called CFD, which is computational fluid dynamics. So simulating what the flow field looks like in that urban environment. And you can see that on the top right video there, where this took about 3 months on supercomputers to process. So it's quite a high fidelity simulation that enables us to understand what the flow field looks like. And we've complemented that with experiments within our wind tunnel facility. So that's what you can see here on the bottom, on the side left there. And that's the scaled 100th scale of the building and the site. And we've done some experiments to try and validate the simulations, but we've also done some full-scale measurements to understand the flow field. And that's part of identifying worst-case gusts or worst-case scenarios in which an aircraft flying through that urban environment or around that building infrastructure, what is the worst condition that it can face, right? And you've got, for example, the concept of air taxis. You are going to be sort of flying very close to and near the rooftops of buildings. So what we predict or expect is that flying through shear layers probably represents one of the worst types of gusts an aircraft can go through, just because of the high magnitude of the fluid velocity, and also I guess the angles as well of that sort of flow field. So what we've done was we've actually developed a drone that we called Narwhal for obvious reasons, Narwhal the whale. And basically this drone is capable of measuring to a high degree of accuracy the flow field in an urban environment. So it's almost like an airborne wind sensor. So this was quite a success. And, we prefer not to call it a unicorn, but this was quite a success. And what we've done was we've actually, I'll click. You can see a video here. So this video shows the drone actually flying on top of that building and basically taking measurements at full scale on the top of that building through the shear layer, and we're using those measurements to try and understand what an aircraft would experience as it flies on top of that rooftop. Now, we're also working towards expanding that concept by flying a number of drones to try and basically get an instantaneous, real-time sort of velocity profile in front of that sort of building, which is useful for a number of applications, including architectural applications. In fact, we are working with the company, an architectural firm, and sort of building that capability as part of that. So moving on from that concept and sort of utilizing that sensing within a control architecture to help not just characterize the flow field, but help reduce the effects of turbulence on the aircraft itself. What we've done was we've installed those sensors in front of on the leading edge of an aircraft to try and see, when we use that as a part of the inner control loop, does it improve things? And the answer is yes, it does. So what we're looking at here, let me explain what we're looking at. The left video and the right video is basically filmed within a wind tunnel facility, and the wind conditions in both of those is identical. So it's typical of a windy day in a suburban environment, and the turbulence intensity is about 7% in there. So what you can see in there is basically two drones that are about half a meter wingspan, and it represents a small drone, small UAV, and as they're both flying in the same conditions. The left aircraft basically has conventional control system, which utilizes and is based on inertial sensors, IMUs, which are basically gyroscopes and accelerometers. But on the right side, it is using that sort of flow sensing on top of that control architecture, and you can see there's a difference in the performance. If you don't know what you're looking at, then you're looking for two things: how much the aircraft bounces around, which you can see the right side, which uses conventional systems. It does bounce around quite a lot compared to the right side. And you're also looking at, for example, the roll, the attitude disturbances in the roll axis. So you can see the wings sort of going between the right and left wing. They're sort of jumping around. Compared to the right side, the image or the video on the right side, it's not bouncing around as much. And that's about 50% reduction in disturbances that we found by just utilizing a system that predicts what the disturbance that's just about to hit the aircraft and sort of accounting for that and actuating the control system before it actually starts moving. So we found that's quite an effective way of doing things, and that has quite a big benefit and advantage for aircraft and air taxis. You don't want these air taxis to crash, right? We can probably afford crashes on roads because it doesn't involve crashing into infrastructure, although depends on who's driving, I guess. But it's quite costly if we have drones crashing, and it has started occurring. So you don't want turbulence to be one of those reasons. And you can see here that phase advanced sensing has quite a drastic effect. So one of the things we found was if you keep increasing the turbulence intensity or the level of turbulence, it gets to a point that even with advanced sensing systems, as you see on the right there, it starts to become quite challenging from the perspective of control authority and rapidity. So the aircraft doesn't have sufficient control authority to account for or to counter the large, gusts or intensity of gusts. And we've seen instances where the aircraft was fully deflecting in one direction, but it was just being overpowered. This leads nicely to what we're then decided to do, was to see whether we can learn from birds. And we found that kestrels, which is the species that you're looking at, they basically have this amazing ability, something called wind hovering, which it's a hunting strategy which involves them basically fixing their head at a sort of spatial position and being able to sort of cope with a lot of turbulence at that stage. What you're looking at here is typically about 7% turbulence, which is what we saw in the previous videos, the two videos that we saw before with the aircraft. And you can see here the bird is really maintaining its position, its head position, to a high degree of accuracy. And they need to do that as part of the hunting to try and identify prey underneath. So crazy idea was for us to try and study that and replicate that in our wind tunnel facility. So what we're trying to do is we're trying to achieve bio-inspired designs that would enable us to mitigate the turbulence in a much more effective way, because aircraft have sort of evolved in a way that would enable them to carry human passengers on board and human pilots. But as we deviate away from that, I think we should start revisiting the shape, and especially with smaller aircraft that don't have that much structural loads, we can start to explore novel shapes and design methodologies. So we haven't been involved in this UAV that you can see here, this red bird-like UAV, but this just shows how we would want to achieve that. And the right place to start is by studying birds. So crazy idea of mine a couple of years ago was to actually, get birds to fly in our wind tunnel facility, train them up, get them to do the same behavior, which, trust me, isn't easy. I learned not to work with I guess I learned my lesson working with animals, and it's not easy because they're not mechanical systems. They've got a mind of their own, literally. So training them to wind hover, as you can see here, and basically subjecting them to different turbulence conditions, different gusts, and characterizing their response using machine learning techniques to try and understand trends in their response. And you can see here the bird is actually flying in low turbulence conditions, and it's doing a lot of correction maneuvers there. And you can see its head is fairly fixed at that point. As you increase the turbulence, remarkably, the head also stays almost fixated to that position to within millimeters, which was quite surprising for us. And it's doing significant amount of corrections, and us deciphering those sort of kinematics and those articulations of the wings and the tail is really the goal, and using AI to try and understand what's going on so that we can transfer that knowledge to drones, essentially. And that is the goal, and that has a huge number of applications. The other aspect, now moving on from turbulence, is energy density. And by utilizing the simulations that I just talked about before, that's around the urban flow field that I showed before, that we've done, we can utilize that to say, all right, well, there are regions for a given wind direction that you'd want to avoid because the turbulence is so high in that. And if you're planning to go from point A to point B, well, maybe best to avoid that location because it's just, it's not wise to do so. And, manned passenger aircraft do that all the time with, getting weather forecasts. So I think it's quite sensible for us to utilize such, technologies and such methodology to try and enhance our path planning rather than just blindly go from point A to point B in a straight line. And what we've done was we've even taken that a step further by saying, well, you've got an obstacle. And what that obstacle does is it blocks the flow. So the flow tends to go up. Now, any upward motion of the flow is very useful for flight because these are sort of pockets of, let's say, free energy. Because an aircraft doesn't need to consume that much energy if there is an upward motion of air. So what you see on the left there is from the simulation that you saw before, these blue sort of regions or bubbles, they represent regions where the flow is going upwards. So we have looked into developing a path planner, and that's part of ongoing research, is to try and see whether, from going from point A to point B, can you deviate slightly towards those blue regions to gain a little bit of energy and reduce your overall consumption. And theoretically, through the simulations, which you see on the bottom right there, where you have a little bit of a glider that's going across our campus in Simulation World, it is possible. In fact, that is an unpowered glider, and it can complete its mission entirely relying on the atmospheric wind and the updrafts. So what we've done was we've utilized that approach by doing the world's first autonomous orographic soaring, attempt, by utilizing that glider. Again, it is unpowered. It does not have any propulsion. It just has a battery on board that powers the electronics that basically tell the drone where to go. And in this specific video, the aircraft was instructed to just stay in this updraft region and gain as much height as possible. And you can see here that it's doing that quite well. So obviously you can't see the wind in the video, but there is quite a substantial wind, and it's in this region, sort of in the windward side of the building. So there is potential and opportunities to utilize and harvest energy from the flow field. Lastly, the stuff that I talked about in terms of noise and the sort of work we do in the noise area. is to try and understand and characterize the noise, I guess the acoustic field and the emission that's coming out of a drone. And what we found is that it is, if you're close enough, then obviously you've got regions that might be louder than others. So if you're standing about 45 degrees away from a drone, you'll probably hear it loudest. But if you're along, in the same blade plane or in the same plane as the aircraft, then that will be the sort of quietest. But obviously, as you start going away, you can start to treat it as a point source. And one of the things we're doing is also adding to that is exploring whether we can create acoustic models for these drones to try and see whether we can include that in the path planning so that what the propagation and noise propagation of the drone is, which means you can probably steer away from residential areas to avoid complaints. So trying to understand that, and what you see on the right side here is basically an acoustic camera trying to, explore the specific regions of the noise source. And we found obviously that, the motors and the electronics, the electronic regulators of the motors, they emit noise. The motors themselves emit noise, but maybe the largest contributor, depending on which frequency, is the propellers or the blades. So one of the things we've done along with an industry partner, I'll just click on next. So one of the things we've done along with an industry partner is we basically explored and used machine learning techniques to try and vary propeller geometries and use that within a feedback loop, basically along with CFD simulations or flow simulations that we can use to predict the acoustic signature of those propellers, and use that in a feedback loop to be able to identify the influence of different metrics on the acoustic signature of propellers, and basically come up with a couple of candidate propellers that we experimentally validate. And what we found was that we were able to reduce the noise of the propeller by about 17 decibels, which was quite a remarkable achievement, because we haven't even explored the full, parameter space of propellers. So that was probably one of the more recent successes that we had, and was circulated in the media recently. But I guess that brings us to the end. So hopefully I've given you a bit of an overview of the different areas that we work in. And if you're interested, you can search on YouTube for Eagle Kills Drone, which shows one of our highest watched videos on YouTube that involves one of experiments we did with that glider, trying to explore soaring and harvesting energy from the atmosphere. But what happened, we were attacked by, the aircraft we were flying was attacked by a wedge-tailed eagle, as the experiment was done in Australia. And this is a 2-meter wingspan eagle that basically decided to grab our drone, fly away with it, and it had about $10,000 worth of equipment. So I had to go the other way of the mountain, the other side, and I'm pretty sure I saw snakes and other dangerous creatures. But luckily I retrieved it. I'm safe and alive. So so if you're interested, just search for Eagle Kills Drone on YouTube, and you should see it there with this thumbnail. But if you're interested more in terms of what we do, you've also got our website there, ruasrt.com, that showcases some of our research. And we, always work with industry partners to try and support them and enable these technologies. So I guess that brings me to the conclusion. Thank you so much. And that's all from me.
Thank you so much, Dr. Abdul Ghani.